All right, here we go. Real calculus. A lot of you have seen this before. If you came from pre-calc trig honors, you haven't. If you came from intro to calc, you have. So I am going to keep moving relatively quickly. We've also done this lesson already. So if I were to do this in class, I would probably double it up with the next one. I like my quote. When I was a child, I spoke as a child, but when I became an adult, I put away childish things. And I like that because that's what derivatives is. It goes from this little baby math, even something as complex as trig, doesn't compare to calculus. So make sure you get the first one. Understand the definition and notation of a derivative. It's everything, and not just how to take derivatives, the definition and notation. Understand the relationship between function and the derivatives. That's a piece of cake. Understand when derivatives are not defined. Well, that goes back to unit 2 with continuity and limits, things like that. Use the calculator to find derivatives. That's a piece of cake. Reminds me, I don't think I have one handy because someone stole mine. Hope I don't need it for this lesson. If not, then I've got work to do. And understand the relationship with continuity and derivatives. That's kind of goofy, but not a big deal. Then calculate derivatives of functions, polynomials, blah, 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 blah. We're going to do products and quotients. That's when things get kind of goofy and tricky. Apply derivatives to velocity, speed, and acceleration, and we're going to do derivatives of trig values. So that's tricky stuff. It's hard work. So first step, derivative of a function. Already did this. There it is. Now we're calling it a derivative, and we're changing our notation. We don't say m. We say f prime of x or dy dx. I believe this is Newton. I believe this is Leibniz. Okay? Important you understand that. And important you understand that it is still slope. Nothing's changed. We're just calling it a derivative now. All right? So what's another way to describe the derivative of a function? It's just slope at a point on the curve also known as the tangent line. All right, we get into domain, doesn't matter, but domain of the derivative might be smaller than domain of the function. Function is derivable at every point on its domain is called a differentiable function. Yeah, no kidding. So find the derivative, right? Now let's go short way, which we're getting closer and closer to being that's the only way we do it. 3 comes out front, subtract 1. And we would say f prime of x, 3x squared, or dy dx, 3x squared. One of the 5 or 6 big things they want you to be able to do is be fluent in notation. I think I just mentioned that a minute ago. So make sure you can. Here's the long way. Which, if you want to blast it out, I believe will get you x to the third plus 3x squared h plus 3x h squared. Oops. Plus h to the third minus x to the third over h. Sorry for the mess. Which the x to the thirds cancel. All the h's pop out. Plug in h equals 0. See ya. 3x squared. Shocker. That's it. That's it. Right, that is it. So many people, I don't know what just happened. There's nothing to get into. Here's what x to the third looks like. What's the slope of the line? at 1. Three times 1 is 3. That's it. Can't keep saying that's it. People just don't want to understand it, or it takes a little while. So we'll get there. Now, some of the ways derivative is notated is f prime of x. Now, I want to make sure I'm clear about this. D dx of y, which we typically write dy dx. You're probably like, that's nice. I'm still confused. What's going on? You might want to understand this. Because if I have an equation, y equals x to the third, I'm really applying the derivative function to both sides, d dx, and I'm getting dy dx equals 3x squared. Boy, oh boy, oh boy. Sooner you can lock that down, the happier you're going to be. So, hey, I know another way to do the derivative. Well, who cares? I get the same answer. Yeah, I know, but I got a job to do here. So, what if we use this other definition? Well, that's not really going to pop up. Yes, it is. They do this every now and then. So read this for a second. They're basically saying, just call this x. How do they do it? F of x minus f of, no, call this a. Call this x. So, oh yeah, how do we find that tangent line? F of x minus f of a, there it is, over x minus a, there it is, as x approaches a. So not as h goes to 0, but as x gets over here and becomes a. Okay, that seems weird. Well, wait a minute, we got this. Y equals root x. Yeah, how about we cheat over here and do the short way? Y equals x to the 1/2. Therefore, y prime, I like dy dx personally, y prime, they did put a prime up here. Should I put y prime of x or just y prime? Doesn't matter. Equals 1/2 x to the negative 1/2, also known as 1 over 2 squared of x. Wow, this would be so fascinating if it actually works out that way. F prime of x equals limit as x approaches a, square root of x, square root of a, over x minus a. I don't like it when I do that with my a's, but I do it way too often. I have no idea what to, how about a conjugate? Let's see if that helps at all. You say so, you're the boss. Limit x approaches a, root x times root x, x middle terms cancel, minus root a to a. Kill. See ya. Wait a minute, why didn't you just put x equals, oh, because it becomes 0 on the bottom. Oh, that's stupid. All right, as x approaches a, so put an a there, which is 1 over root a plus root a is 2 root a. Doggone it, why do I keep doing that? As x approaches a. Well, isn't that weird? Math, cool. All right, let's understand how derivative of the slope of a tangent line. Look at the relationship between, yeah, whatever. All right, what's the slope here? Right about 2. Slope is 0. Oh, look at that, it's 0. What about here? Big hint, I typically go for those zeros first, both forwards and backwards. Huh, check it out. Almost like somebody lined these up so that you can like look at them right on top of each other. Very cool. Let's see, right here. Really freaking big. I mean, let's see what I got here. 1, 2, so it's 3, 4. Yeah, it's about 4. 1, 2, 3. Wow. All right, in all seriousness, I did not do that on purpose. How about here? Pretty close to 1. Well, it's down. It's pretty close to -1. Yeah, pretty close. So m equals -1 ish. M equals 4. Sorry, I know I've been writing off the graph there. So that's your function. That's your derivative function. They're both changing all the time. Want a big hint? Peak valley. X squared has 1. X to the third with a lump. So this is like an x third, kind of. And this is like a x squared, kind of. Oh yeah, I get it, because when we take derivative of 3 and we subtract, oh, okay. So yeah, I mean, there should be a 3 out here front, or yeah, whatever. Just getting a general idea. One peak, one valley becomes one valley or one peak. Oh yeah, that makes sense. Boy, I swear we might have spent time on this in pre-calc. Yeah, probably not. Okay. Let's have some fun. Sketch a graph of f where f naught equals 0. F prime of x equals what? With x minus 1 or x minus 1. Well, that's my f graph. It's my f prime of x graph. And I've seen this one before. If I plug in 0, I get -1. I plug in 1, I can't get anything. So I have a hole there. If I plug in 2, I get 1. Sounds familiar. Okay, sure. So now we're going backwards, Mr. T. I'm dying here. Well, starting at 1, it's continuous. That's important. The slope is always 1. So the slope is always 1. So that just means it's always 1. So I could just draw a line like that. But I'm going to make it continuous. Let's see what's going on. Slope is always -1. So something like this. It's not defined there. Yeah, that's okay. Domain can be bigger of the function than that. We already said that. Oh, that's very cool. Can I take the derivative here? No, the slope on the right and slope on the left are not together. I can't take a derivative when we don't have a smooth curve, cusp or corner. It doesn't really work. So neat. Also graph a derivative using data. There's probably that 2 people in a room share the same birthday. Now I wanted to throw this out, but it is so cool. If there's 30 people in a room, there's a 71% chance they share the same birthday, which is like, what? That doesn't make any sense at all. All right, so this is called numerical. Don't get hung up on it now. But look at that, delta y over delta x. This is important that you understand this. And forget the math, just look at this. What's going on here? So go to 5 and approximate it going with 0.117 over 0 divided by 10. Oh, look, 0.0117. So that's a slope function, change in y. We're doing a rock from here to here at 5. Sure, whatever you say, man. I don't know why you're doing that. No, you don't have to know why. Only I need to know why. We're taking a derivative of this function and over here. So we can approximate it numerically. Cool. That was Leibniz genius. Delta became this. Lowercase delta. And we bastardized it into that. Delta, good size gap, gap's 10, midpoint's 5. dy dx, infinitesimally small gap. Oh, so we'll just write as dy dx. So here's how you approximate things. If I were to ask you, well, give me derivatives of this. Well, you didn't give me enough data. We're going to do this, so don't get hung up on it. It's just a rock. All right, well, 10 minus 0 on the bottom, 0.1 on the top, 0.411 minus 0.17 over 10 on the bottom. About what's going on in the midpoint of those two. Okay. That's why I leave it up there, so I can tell this story. Now, what do the graphs look like? Well, that probability thing is kind of cool. The function says when there's only no people in the room, 0 people in the room, my chances of people having the same birthday is 0. But then it gets better and better and better, but it never actually hits. It's called the logistic curve. We'll come back to this later. And the derivative says that the most rapid change happened right here, around about 20 people. Whereas we got to 20 people, my percentages were increasing the most right about 20. I'd probably draw a line right here and say that's about where things kind of slowed down, but it doesn't matter. Just giving you a taste. Really gonna do more of this. All right, just like limits, we could take one-sided derivatives. It is not on the AP exam. It is not on one of my exams. But we should just be clear about it. So let's just practice one of the last few times we're gonna do this little stupid limit thing. So from the left, it would just be this. But from the right, and believe it or not, I actually have a reason to show this. I like this. And the reason is several people told me they get to college and suddenly a professor makes a big deal out of stuff like this. So I got to give you a taste. Just so you're not like, I don't know what the, oh, wait a minute, Mr. T mentioned something about this. It's kind of pathetic, to be honest. And it is. Bye. So we can do derivatives from both sides. All right. Now we would also say, based on that information, the derivative does not exist because it has to be the same from both sides. So that's actually the best reason I probably can think of to show you this. Hey, does the derivative exist there? Well, I went limit on the left, limit on the right, does not exist. That's enough for now. Get your head spinning. Good luck and happy mathing.